In section 10.1, we just cover a small part of it, a small part of 10.1 and 10.2 on a certain type of improper integral. And certainly you will see why we call it improper, because at first you just won't see what this could possibly mean. Here we are taking the integral from 1 to infinity, and that's the kind of integrals we're going to talk about, the ones that we try to measure the signed area from 1 to infinity. Well, think about this one, 1 over x squared. If you think about that area, I think most of us in our logical thinking would imagine that this doesn't make sense, because there's an infinite column of area there. So what would you say that the integral would be? What would the signed area be? It seems like it would be infinite, doesn't it? But it isn't. The area under that curve. We're not changing any definitions of the integral. It still means signed area, and that signed area is finite under this particular curve. And I want to show you how we can define that. Let's take, I guess I'll go to yellow. Let's just say, I don't know how to get a signed area from 1 to infinity, but I could just chop it off somewhere like right here and call that t. I do know how to find the integral from 1 to t of 1 over x squared dx. That's entirely reasonable. That's what we've been doing up until now. And then I'm just going to drag t to infinity. In other words, I'm going to take the limit of this function of t. That's a function of t. I'll find it, and I'll take the limit as t goes to infinity. And if that limit exists, that's what we will call the improper integral from 1 to infinity of 1 over x squared. So, well, let's see, that's x to the minus 2. So minus 1 over x evaluated between t and 1. I'm going to take the limit of that as t goes to infinity. Now notice, I've got to get the x's out of there. I have to get this to be a function of t before I can take the limit. So that would be the limit as t approaches infinity of, plugging in t, minus 1 over t minus 1 over 1, which is 1. And as t goes to infinity, we know that 1 over t goes to 0, and so our limit is equal to, this should be plus 1, shouldn't it? Minus 1 over x, so we have to minus a minus, and so we get 1. And indeed, this blue area is 1. So this is the definition of this type of improper integral. And whenever we have a definition, that means that you should learn exactly what the definition says, and you should know the vocabulary associated with it. Let f be a continuous function on some interval a infinity. Then the integral from a to infinity of f of x dx is the limit as t goes to infinity of the integral from a to t of f of x dx, if that limit exists. If it does exist, we say that the improper integral converges. And if it doesn't exist, we say that it diverges. And that would mean that the limit would be infinite, or just simply not exist. So let's apply this definition to the integral from 1 to infinity of 1 over x dx. It's improper, and of the type that we learned the definition for. So I will just immediately start with the definition. The limit as t approaches infinity of the integral from 1 to t of 1 over x dx. So I need to before I worry about taking the limit, but I don't take the notation away. I need to now take the limit of 1 over x. Oh, that's natural log. And we're all positive here, right? We're on the interval 1 to t, and t is greater than 1. So this is just natural log x. You could put the absolute value signs on if you want. Evaluated between t and 1. I'm not ready to take the limit. The limit as t approaches infinity, I must turn this into a function of t. Well, that's natural log t minus natural log 1, which is 0. Well, so we're not in luck here. The natural log function grows. It goes to infinity, and so this limit we could say equals infinity, but we don't need to. We just say that the integral 1 to infinity 1 over x dx diverges. In other words, really, this as far as a mathematical object, we would never use it. It doesn't have any meaning, really. Okay, let's do one more example. The limit from 1 to infinity of 1 over 1 plus x squared will be, just put in the definition, the limit as t approaches infinity, the integral from 1 to t of 1 over 1 plus x squared dx. And when I look at your homework, if all of the notation is not there, then I'm going to take points off because it won't read right. It won't make sense. Won't be using the definition. So the limit as t approaches infinity of, well, that's nice, we know that, it's arctan x evaluated between t and 1. We're not to a function of t yet. The limit as t approaches infinity of arctan t minus arctan 1 is, now I can take the limit. It is equal to pi over 2 minus arctan 1 is pi over 4. So it actually does converge, and it converges to the number pi over 4. In Chapter 11, we're going to be using these improper integrals, but we won't be concerned about what they converge to. We will just be concerned with whether or not the limit exists. This is a comparison test for improper integrals, and it will make perfectly good sense to you. Draw a picture so that it does make sense. We're saying here we're trying to find out if what functions trap a finite amount of area under them. And here we have an f of x. That's f. And let me make g maybe green. We have g on top. So that's g, and the one underneath is f. And we're integrating, well, 1 to infinity. Okay, so let's just say this is 1. We're integrating from 1 to infinity. Now, if you just, or I guess a to infinity. Sorry, this should be a here, I guess. So we look at this and just look, you could draw the conclusions right now. If g of x gets down on that x-axis fast enough to trap a finite amount of area, in other words, if the improper integral of g converges, then of course the improper integral from a to infinity of f converges. And if f diverges, if f does not get down fast enough on the x-axis to trap a finite amount of area, then because g is on top of it, certainly it will not either. So this will imply that the integral from a to infinity of g also diverges. Now, why would we need this? Well, because sometimes we don't know an antiderivative. We can't calculate that limit that we need to using the definition. So instead we can create an inequality and use the comparison test, or the comparison theorem here. So if we think that an improper integral of g converges, but we don't know how to find an antiderivative for g, then we might create an inequality and find a function f over g that is above g that does converge, and then we would get f of x converging. We would not know to what number it converged, but at least we could get it converges. Now these limits, these functions, these set of inequalities here, I think we talked about those in our section on limits, and you should know these. These are so handy. The natural log x grows slower than nth roots. In fact, these right here, these are just powers of x. Natural log x grows slower than positive powers of x, and powers of x grow slower than exponential functions. So keep those inequalities in mind. What if we were asked to, if the integral from 1 to infinity of 1 over the square root of x squared plus 1 dx diverges or converges? Well, maybe the way to look at this is just throw out numbers like 1 in your mind. When x is 10 million, do we really care if we're adding 1 to x squared? So just kind of throw out the 1 in your mind, and you think, well, this is kind of like 1 over the square root of x, 1 over x. This is similar to 1 over x, and I know that the integral from 1 to infinity of 1 over x diverges. So I'm thinking maybe I could get an inequality here. I don't know how to integrate that. So I don't know an antiderivative. So let's see. Let's look at the square root of x squared plus 1. We know that that is bigger than x, isn't it? So if I take reciprocals, I get 1 over the square root of x squared plus 1 is less than 1 over x. Darn, I was hoping it would be underneath it. Sometimes I don't see an error until I start working it out for you guys. I don't mean to have x squared plus 1. Let me go back up here and change this to minus 1. Okay, just for purposes of the example. Change that to minus 1. Well, and then let's start over. The other example was fine. It just takes more, it doesn't fit the comparison test that I wanted. I wanted you to see an easy example. Alright, so let's take the square root of x squared minus 1. I know that that is less than x, because we're talking about positive numbers, greater than 1. The square root of x squared is equal to x, so if I make what's under the radical a little bit smaller, I can say this. Now, if I take reciprocals then, 1 over the square root of x squared minus 1 is greater than 1 over x. And the integral of 1 over x dx from 1 to infinity, we proved, diverges. Well, this function is over it. So if 1 over x if 1 over x doesn't get down fast enough to have a finite area or to converge, then we know we can say, so the integral of 1 over the square root of x squared minus 1 dx also diverges by the comparison test. Or did I call that the squeeze theorem or comparison test? Either one is fine. You could just say by comparison. Let's look at one more example. if you were given the integral from 2 to infinity of 1 over natural log x to the fourth dx. Well, you don't know an antiderivative for that. And it looks like natural log x, like if x is equal to 100, then if you're trying to compare these, I'd like to get this above 1 over x, which would give me divergence. But if x is 100, natural log of 100 to the fourth power is about 450. So it's bigger than x. But we learned that powers of natural log will eventually be overtaken by powers of x. Powers of natural log x will eventually be taken over by powers of x. And I graphed this on Mathematica to show you. This is at about a little bit before 6,000. You see that this is natural log x to the fourth, that x surpasses it in value. They cross, the two graphs cross there, and then x clearly is above the natural log of x. And hey, we're talking about limits at infinity, so we don't care if it happened at x equals 10 or if it happened at x equals 6,000. It doesn't matter. So what I could say here is for large enough x, for large enough x, in parentheses, let's say x greater than 6,000, we know that natural log x to the fourth is less than x, which gives us 1 over the natural log of x to the fourth is greater than 1 over x. And the integral of 1 over x from 2 to infinity diverges. Therefore, this also diverges by, I'm forgetting what I called it, I'll say comparison test. And that's because that we were able to create this inequality and say that it is true for x beyond some point. I guess I had one more example here. Show that the integral from 1 to infinity, the improper integral of e to the minus t squared dx converges. Well, you know that we don't have an antiderivative for that, so we need to compare it. Well, if it were just e to the, let's write that out, 1 over e to the t squared. I don't like negative exponents because I can't think about them clearly, so I rewrite it this way. Okay, so how does that compare to 1 over e to the t? We're making the denominator smaller, aren't we? We're making the denominator smaller. Everything's positive. So if we make the denominator smaller, we grow the fraction. If we make the denominator smaller, numerator is the same, everything's positive, and we shrink the denominator and thus grow the fraction. So I would say this, and the integral from 1 to infinity of 1 over e to the t, which is e to the minus t, let's put x's in. Doesn't matter, but I'm going to use our definition. E to the minus x dx is equal to the limit as t approaches infinity, the integral from 1 to t of e to the minus x dx. Well, let's see, I need a little adjustment. I need a factor of minus 1 there. And now I have e to the u du. So this will be equal to the limit as t approaches infinity of, and now I integrate. E to the u du is e to the u. E to the minus x, and it's minus e to the minus x, evaluated between t and 1, which gives me the limit as t approaches infinity. I can't take the limit until I have a function of t. So that gives me what? That is, by the way, minus 1 over e to the x. So I'm going to write it as minus 1 over e to the t, plugging in t, and then it will be minus a minus, so it'll be plus 1 over e to the 1, which is 1 over e. This limit here is clearly 0, denominator growing, numerator constant. So that is the limit of 0, and this converges. We could say equals 1 over e, but I don't care what the value is. I just needed to know that it converges. So now my statement is, my conclusion is, 1 over e to the t squared is less than 1 over e to the t, and we just proved that the integral from 1 to infinity of e to the minus t dt converges. Therefore, so does the integral from 1 to infinity of e to the minus t squared dt by our comparison. I'll put comparison test. It's not really called comparison test. Comparison theorem.